This study on ferromanganese deposits offshore Southeast Africa came about because Wilfred Jockers and I were attempting to dredge the Mozambique Ridge in order to resolve whether it is oceanic or continental in origin. Although we collected some rocks, we also collected a lot of ferromanganese deposits and therefore initiated this study. Sam came on board as a postdoc study, Warren continued with studies for an MSc, Maria undertook some micropaleontology studies, and Errol undertook the bathymetry and substrate studies. The Mozambique Ridge is about 1,500 kilometers long. It's close to onshore in Mozambique, but by the time it comes to the south, it is some 400 kilometers offshore and is about 300 kilometers wide. To the west is the Natal Valley. This is where the Falkland Plateau slots in when you reconstruct Gondwana. This plateau was pulled out during the breakup of Gondwana as South America moved away from Africa. So the Natal Valley is underlain by oceanic crust. Mozambique Basin is also oceanic crust produced when Antarctica moved away from Africa. In between is the Mozambique Ridge, which we now consider as having formed as a large igneous province during the breakup of Gondwana. And it's possible to reconstruct the topography of it at various times. Here's a snapshot at 135 million years ago, where the northern end of the ridge had already submerged, whereas in the south there were oceanic islands up to 2 kilometers high. So essentially the ridge was a volcanic archipelago during Gondwana breakup. There are three main environmental factors that control the chemical composition of iron manganese encrustations and nodules. There's the primary productivity in the surface water. There's the oxygen minimum layer within the water column. And then there's the calcium carbonate compensation depth. If we do a cross-section at about 33 degrees south, you can see the Natal Basin, the Mozambique Ridge, and the Mozambique Basin. And the oxygen minimum layer encompasses the top of the Mozambique Ridge. The carbonate compensation depth occurs at depths in the Mozambique Basin. This combination of topography and the water column has given us three types of deposits: the ridge crest, the ridge flank, and the basin deposits. So we look at the general compositions of these three types of deposits. You can see where manganese, iron, and cobalt all have a Z shape. At the ridge crest, there's quite a range of compositions. Between the oxygen minimum zone and the carbonate compensation depth, there's a gradual decrease in the elements, and there's a little kick just below the carbonate compensation depth. Nickel has more of a C shape, and copper has an L shape. Now, although this table is showing averages, it's worth looking at because it gives you the sort of values that you find. Manganese and iron are somewhere sort of 10 to 20% in these deposits. Cobalt is 0.5% or less. Nickel usually around about 0.5% or less. And copper is an order of magnitude less than that. The origin of these deposits: there are three principal modes of formation. There are hydrogenetic deposits. These are formed through direct precipitation of metals from seawater in what is possibly the slowest chemical reaction on the planet. There's a diagenetic origin, also direct precipitation of metals from seawater, but also remobilizing metals from the underlying sediments into the deposits. And finally, there are the hydrothermal deposits formed from circulating hydrothermal fluids. Notably, these occur on mid-ocean ridges. In the case of the Mozambique Ridge and Mozambique Basin deposits, most of them are hydrogenetic growth with some diagenetic growth of nodules. Something that we discovered during this project was there's nanoplankton interlayered with the iron magnesium laminations. This is an encrustation enclosing pre-existing rock, and within these are very fine laminations. You can find nanoplanktons, the same in the nodules if you break them open. There are 61 species that have been identified, and they show a bimodal age. They're either Pliocene in age or they're Pleistocene in age. Because we can take the oldest incrustation layer, and we know the thickness of the layer, we can calculate out the rate of precipitation. And they range from more or less 5 millimeters per million years to about 250 millimeters per million years. The latter is very high for hydrogenetic deposits. Now, it's a little bit of an enigma that these deposits have formed in the last 5 million years, and yet we have a ridge which is 155 million years old in places. The solution to this is probably in the oceanic water itself. This is a schematic diagram showing ocean currents from 30 degrees south to 60 degrees south between southern Africa and Antarctica. All the currents of whatever depth you're at are actually flowing to the east. The exception here being water coming out of the Weddell Sea, some of it going back into the sea itself and some going northwards to form the Antarctic bottom water. But there's also an interloper from the northern hemisphere that comes in here, North Atlantic deep water. Now, how does this relate to what we're seeing in this area? Well, Antarctic bottom water comes up the Mozambique Basin. North Atlantic deep water comes up the Natal Basin, and then it either goes through the ridge or swirls around and comes around the southern part of the ridge. The North Atlantic deep water may have arrived in the Pliocene because of a change in equatorial flow between the Atlantic Ocean and the Pacific Ocean at that time. The Panama Isthmus developed between North and South America, blocking off this equatorial flow between those two oceans and changed the circulation. So this may be a reason why they see the Pliocene development. The Antarctic bottom water, although the Antarctic has actually been glaciated for about 30 million years, may have came further north up the Mozambique Basin during the Pleistocene as we moved into the current ice age. So what potential conservation issues are there should these deposits be mined? This diagram was produced by Nautilus, a company that was well on the way to mining the Bismarck Sea when it went bust in 2018. They undertook a number of studies and produced these summary diagrams. At the bottom, you are actually quarrying the sea floor on what are euphemistically called sea floor production tools. Then you have a slurry which has to be lifted up to a production vessel. Now, quite clearly, if you're quarrying, you're actually destroying the environment and removing material. And as soon as you see the word slurry, you know that you're seeing sediment plumes. Similarly, if you start working with abyssal deposits, although one potential miner rather infamously described collecting manganese nodules as the same as hoovering up golf balls on a driving range, this rather omits the fact that this process produces enormous plumes. There's a collector plume as you're actually hoovering up the nodules, and then a dewatering plume as the material you don't want is being pushed back into the ocean. This is an area full of filter feeders, so any plumes in there is going to cause a big problem. And it's an area where processes move very slowly, as you can see in the precipitation rates of 5 millimeters in a million years. So, mining. There's some political economic considerations here. Firstly, a significant proportion of the iron manganese deposits in this study lie outside the South African economic zone. At present, 200 nautical miles, it just nicks part of the western Mozambique ridge. But if the extension is allowed to take place, the whole ridge and a significant portion of the Mozambique Basin will become South African territorial waters. South Africa has extensive iron manganese reserves onshore. So this makes interest in marine mining for these elements by South African companies unlikely. However, the money spinner in these deposits is cobalt, and there's not extensive deposits onshore. If you look at the overall composition of the mineralization, the nickel, copper, cobalt is 1.3%. The accepted cutoff is about 2%. However, that obviously changes according to economic situations. So currently, even under the nickel, cobalt, cobalt situation, South Africa is unlikely to want to mine this. We've been discussing this ridge here, and you can see that in this area there are lots of other ridges and lots of other plateaus and lots of abyssal plains. And these areas do not fall under any exclusive economic zones. However, there may be lots of ridges, but there's only one blue planet.